Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. This is Adib, a lecturer for Mechanics of Materials Section 3. So in this recording, we'll go to chapter 8, Combined Loadings. Okay. Here we have 8.1 and 8.1 and 8.2. In 8.1, we'll discuss about the stresses developed in thin wall pressure vessels. Okay. Because they are combined stresses. That's why it is included here in the combined loadings. Okay, and in 8.2 we will discuss on the stresses developed in a member's cross section when axial load P, torsion T, bending M, and shear force V occur simultaneously. I mean, we'll combine the previous chapters, what we learned in previous chapters, the stresses, and we'll see on the effect of this combined loadings. Okay, so let's go to the first one, which is the first one, thin wall pressure vessels. Okay, uh, for those who don't know what is the pressure vessels, basically there are two types of pressure vessels. One is this cylindrical, right? Let me change the pointer first. And cylindrical vessels. Okay, and another one is spherical vessels. Okay, spherical is like this shape, while the cylindrical is like this shape. Okay, so we have to make assumptions first. Okay, so basically there are two main dimensions for the pressure vessels. Okay, one is the radius r. Okay, radius r. Another one is the thickness t. All right. So here, this ratio, the inner radius to wall thickness ratio, R over T, it is minimum of 10, right? Which means that the radius is 10 times, at least 10 times the thickness, right? So that's why here we call it as a thin wall pressure vessels. Why we want to make this assumption, the first assumption here, is because we we do not want to consider a type of stress, right? Which we're going to discuss later, right? And the second assumption is the stress distribution in thin wall is uniform or constant, right? Which means that uh, the distribution is uniform, right? So if you cut, for instance, can you see this B? If you cut and you have this distribution, stress distribution here, for instance, these surfaces, you say that they are uniform and constant, right? Simple as that, right? So here you have this either for the cylindrical. Okay, let's go to cylindrical vessel. Uh, we define X, Y, and Z exist. Okay, here we define like that. Then this is your inner diameter R, right? And then this is your thickness, all right? So we have for cylindrical vessels, thin wall cylindrical vessels, we have two types of forces. One is the hoop stress, another one is longitudinal stress. All right, so what are they? We'll look at them individually. So the first one is the hoop stress, which is in the hoop direction or circumferential direction. How do we get that? This is the cylindrical vessels. Okay, so we make three planar cuts. Can you see the first one? This is the first cut, second cut, and the third cut. So this is the resulting section that you will get when you do these three planar cuts. Okay, and then look at here. What happened here is that as you have this P is the internal pressure of the vessel, right? For instance, you have pressurized gas, for instance. So this pressurized gas will have this P, internal pressure, right? So you will have this sigma 1 acting on these cross sections, this and this cross sections. Okay, of course the rest are just dimensions. These two R is diameter, right? and then you have the thickness, right? And then you have this dy. Why dy? Because this is y direction. Okay, this y direction. Dy is the differential y, differential length of y. Okay. So if you do summation of forces in x direction, okay, can you see this is x direction equals to 0 because this is in a static equilibrium, right? So you'll have the force due to the sigma 1, okay, times this area, which is t times dy, right? The area. And then you times 2. Why times 2? Because you have two areas. One here and one here, right? I mean, you have two forces. And then this is the positive, and then you have the negative force in x direction, which is this one, P, right? The internal pressure. Internal pressure, this is the pressure, you have to find what is the resulting force. So you multiply this P with this area, okay, this area. So what are this area? What is this area? R times dy. As simple as that. And then you simplify this, you will get sigma 1 equals to PR over P. P is internal pressure, R is the radius, and T is the thickness. Okay, and this is the hoop direction stress or hoop stress or circumferential stress, right? Circumferential. Can you see that this is circumferential direction? This circumferential direction, right? So this is the first type of stress for the sneaker vessel. Another type of stress is the second type of stress in circumferential is you do just one cut, right? Just one cut, and then you will have this section, right? So what happened here? What happened here is you will have forces, okay, going this direction, right? And then what happened to this area? The cross-sectional area of the tin, the wall, the vessel's wall. So you have this sigma 2, right? This one is, we call it as a longitudinal stress, sigma 2. Okay. Here you do the forces, summation of forces in y direction equals to 0, equilibrium. Okay. And then it will be sigma 2 times this wall area. Understand that? The wall area. The wall area will be what? This circumference, right? 2 pi r, this circumference, times the thickness t. Okay, so this is the area, 2 pi r times t. Alright, so it goes positive here. And then on the other hand, you have the force as well due to the internal pressure P. Okay, and this internal pressure P will act on this area, right? The area inside the vessel, which is what? Pi r squared. Simple as that, isn't it? Pi r squared. Why pi r squared? Because this is a circular cross section with radius r, right? And then you manipulate this equation. I mean, you simplify, and then you will get your longitudinal stress sigma 2 equals to PR over 2T. Again, it is P, internal pressure, R is the radius, and T is the thickness. And you have 1 over 2 over here. You realize that you have longitudinal stress here, sigma 2, okay? Longitudinal stress is sigma 2, which is half of the previous one, the hoop stress. Notice that, okay? So keep that in mind that for the cylindrical vessels, your hoop stress due to the P, right? Due to the internal pressure P, your hoop stress is twice as much as your longitudinal stress, right? Okay, before we go here. Okay, let's go to the second type, spherical vessels. So spherical, okay, spherical at the bottom, right? Where you have the constant radius all along. Here you can just have one cut. I mean, at one time you just have one cut. You do one cut, right? And then you do the longitudinal, like the one that we did in the previous slide, okay? This longitudinal sigma 2, okay? And then you will end up with sigma 2 equals to PR over 2T. Okay, for any card, it will be PR over 2T because you just have the longitudinal stress. You don't have hoop stress, right? Okay. So before we go to the example, actually there is another type of stress here. We call it as the third type. People call it sigma 3. Okay, but this type of stress is a radial. Radial means that, for instance, can you see that this one? It goes radially, following the radius, right? R, you see this R radius, okay, from the center to the wall. So this one, the third one, sigma 3, right? This radial, okay, is a radial stress. We have this as well. And actually, can you, if you understand it correctly, if you have kind of zero pressure, let's say let's put it kind of very small of zero pressure outside the vessel, and you have P, internal pressure P, inside the pressure vessel, can you see that actually this on this inner wall you have P. I mean, this sigma 3 will be P, right? On, and it will vary until it reach the outer wall, which is the atmospheric pressure of 0, right? I mean, depending on, I mean, how big the pressure inside. I mean, the atmospheric pressure is quite small, okay, compared to what usually the pressure inside the pressure vessel. So usually we set it from this to 0, though actually it should be from P here inside to atmospheric pressure, okay. But the thing here is that as we say that this pressure is P, I mean the biggest pressure of radial stress is P. So can you see that this equation, for instance, for this longitudinal stress, PR P R over 2T, right? Can you see that this one will magnify the magnitude of the stress? And we say that for the thin wall pressure vessel, the R over T is more or equals to 0. Sorry, 10, right? Which means that here, at least, if in this case, it is 5 times bigger, right, for this longitudinal stress. While for the previous one, the hoop stress will be 10 times bigger. Can you see this equation? 10 times bigger than the P, right? At least. Okay. So that's why in the case of the thin wall, right, this R over T at least 10, the ratio of R over T is 10, which means that the wall is quite thin compared to the radius, right? So the effect of the radial stress is very small, all right? It's insignificant. So we can ignore the effect of the radial stress sigma 3, right? Okay, so we go to one example for this. Okay, we have this. The question gives you the spherical pressure vessel like this, right? Which has inner diameter of 1.2 meter. Okay, inner diameter, not inner radius, right? 1.2 meter, and a thickness of the 12 millimeter. So basically, your R inner radius is 600, right? 600 millimeter, while your T here is 12 millimeter. You can start calculating actually. This 600 over 12, the ratio is like 50, right? Can you see? Can you imagine now? If you have a certain pressure inside, the stress developed in the longitudinal or the hoop directions, there will be at least 50, 25 and 50. respectively, right, from the pressure itself, right? So the question asks to find the maximum internal pressure it can sustain, okay, find the maximum P, so that neither circumferential or nor longitudinal stress component will exceed 140. So we say that sigma 1 and sigma 2 or sigma 2 should not exceed 140 megapascal. So this is the maximum stress that we allow for this material. What is the reason behind that? Because basically we say that this is allowable stress for this kind of design, right? So we'll go to this one first, and then we'll go to the spherical vessel, right? So actually it's quite simple. I mean, in this case, remember that this is a cylindrical pressure vessel. So we have this hoop sigma 1 equals to PR over T, and longitudinal sigma 2 equals to PR over 2T, which is half of the hoop, right? And then you have this diameter, like I said before, you have thickness, and then this is your allowable stress for this material, which is 140 megapascal, right? So which one you want to use? Hoop or longitudinal? If we understand this, actually we need to evaluate for the cylindrical pressure vessel, we need to evaluate the hoop. Why? Because for a given P, same the internal pressure P, you will have the hoop direction, hoop stress to be bigger than the limiting stress, right? Which means that hoop stress will be which is generated, hoop stress will be bigger, will be larger than the generated limiting stress, right? So you have to evaluate this. Sigma 1 equals to PR over T. And then you put this sigma 1 value, the hoop stress value as 140, which is the allowable, right? You say that should not allow, should not be more than 140. And then this is the P, the maximum P that you want to find, okay? And then the radius is 600 millimeter, right? And then the thickness is 12 millimeter. You solve this and you get the maximum internal pressure P to be 2.8 megapascal. And actually you can check if you put this value 2.8 megapascal, and then the longitudinal one will be 70, right? I mean, you can put it like this, or you can put it directly from into the equation. I mean, because you say that you know that the maximum sigma 1 is 140, you can just divide by 2, right? And this is just a check, okay? This is just a check. I told you that you have the third one, the radial stress, right? So the radial stress will be the P itself, right? Which is 2.8 megapascal, right? Can you see that the sigma 3, which is the P, 2.8 megapascal, because of the ratio of 50 here, R over T, the ratio of the radius over thickness ratio of 50, which is quite big. So this P1, which is 140, and sorry, not P1, sigma 1 is 140, and sigma 2, which is 70, they are very much bigger compared to sigma 3, which is the radial stress. Okay, that's why we say that in the case of the thin wall, the sigma 3 we won't calculate because it is insignificant. It's not like they don't have sigma 3. Yes, they have sigma 3. Sigma 3, the radial stress is there, but it is very small, very insignificant compared to these values 140 and 70. Okay. Okay. So next we go to the next thing. The question asks, what happens if you have the same conditions, right? Same conditions means that you still have the same internal diameter of 1200 millimeter diameter or 600 millimeter radius, right? And the thickness still same thickness of 12, like this cylindrical pressure vessel. No, sorry, spherical pressure vessel, right? So if you have the same dimension of R over T, but now it is spherical. So what happened to the maximum internal pressure? So as you can see here, because in the case of spherical vessel, you just have sigma 2. Okay, you just have the longitudinal stress sigma 2, which is PR over 2T. So you, in this case, your 140 megapascal will be the allowable stress will be sigma 2, right? And then you put the rest, and then you end up with this pressure of 5.6 megapascal, which is twice this value, the maximum pressure of the cylindrical pressure vessel, right? The spherical will be twice. Okay, so you can conclude that the spherical vessel can carry twice internal pressure compared to the previous cylindrical vessel, given the same design, the same condition of this R and T, right? The radius and the thickness. Okay, that's all for the first part, right? So we go to the next one, 8.2. So before we go to 8.2, let's have some review on the stress analysis that we have done before. First, in chapter 1, you learn about normal force, which leads to uniform normal stress. This is the equation, right? The normal force divided by the cross-sectional area give you the uniform normal stress. Chapter 1, and even in chapter 4. But chapter 4, it focuses more on the deformation, axial deformation. But basically, it is the same. I mean, you see this formula, sigma equals to P over A, okay? And this is uniform normal stress, okay? And then how about shear force V? What will shear force V do to the section? So what happened is that you learn this in chapter 7 about the transverse shear, that you will have, due to the shear force V, you will have the shear stress tau, right? And the equation is VQ over IT in chapter 7, right? And you have this shear stress distribution. It's not just a uniform anymore, no. This is a distribution, which means that you have different values of tau depending on the location across the section, right? And then the third one is how about bending moment M? Internal bending moment M. You learn this in chapter 6, right? The sigma equals to the fracture formula. Sigma equals to minus M over I. M is the bending moment, internal bending moment M. Y is the location from the neutral axis, right? And then the I is the moment of inertia of the neutral axis. And then you have the longitudinal stress distribution. Again, it's a distribution, all right? Distribution because you have sigma here for this one due to the bending moment. The normal stress sigma, the bending stress, will be 0 at the neutral axis, and it will increase linearly either in tension or compression depending on the direction of the moment, right? And then will reach the maximum at the most furthest distance, right? You have learned this. So can you see that now you have two normal forces? One is here, the other one is here, right? And then the fourth one is you learn about torsional moment T, right? In chapter 5. So if you have torsional moment T, you will have across the section, so you will have this shear stress distribution of tau, shear stress, right? And our discussion in chapter 5 was constricted just to the circle shaft, right? And it's given by this formula. Now you have two normal stresses, sigma, and two shear stresses, tau, right? What happens if you have more than one internal loadings like this acting on the section? So you will definitely have this resultant, right? Resultant stresses. So to solve this, you need to use the superposition, okay? But you don't just add them out, okay? You cannot do that. There are things that you need to be careful because of the location and which direction is it positive, tension or compression, or even in the tau, the shear stress, whether it goes this way or that way. So you need to be careful. But generally speaking, you need to use the superposition principle, right? So this is what we discussed about the state of stress due to internal normal force P. So you will have internal bending moment M, okay, like this. Can you see that the bottom, this is a neutral axis, right? And then at the bottom you will have tension, at the top you will have compression, right? Given by this equation, the texture formula, right? And then the thing is that if you have both P and M, okay, so you need to superimpose them, right? Same goes to internal shear, transverse shear V. So you'll have the transverse shear stress tau, right? And then again, if it goes this downwards, that is V. So you have this neutral axis, right? And then it will be maximum at the neutral axis, and then it will be zero at the furthest distance, right? Not furthest distance, I mean at the okay, let's put it at the most top, right? Or the most bottom. Okay, and then torsional moment T given by this equation. Okay, so basically for these two, you can superimpose them, but you have to look at the direction, right? So let's look at this simple example 2.2. Here you have this member, right? Like a column member. You apply 15 kilonewton load at this point, which is not at the centroid. Centroid is here. Okay. And the question asks you to find what is the state of stress at this point B and this point C. Okay, and then you have this dimension, like 50 and 50 from the left to the right, to the 50 to the centroid, and to the right 50. And you have 20 and 20. All right. So first thing first, determine the state of stress. What kind of stress? Is it normal or shear? We won't know this until and unless we do the cut section. So you cut not through the point BC. No, we cut through the section. You section this through the point, right? So you cut. When you cut, see this cut, and then you can see that if you have 15 kilonewton load, right? And then because this one will have it has an offset, okay, distance with the centroid, this axis, so you will have this internal bending moment as well, right? Going this way, right? Why is that so? Okay, this is statics, so you have to check again how actually it works, right? So what happened here? Due to this 15 kilonewton internal load compression, you can simply find the normal force, right? This 15 kilonewton divided by the area, which is 100 times 40. 100, okay, 100 times 40, okay? Simple as that. And then you have this compression, uniform compression of 3.75 megapascal, right? On the other hand, due to the M is 750 kilonewton millimeter internal moment, okay, you will have this normal stress as well, but due to the M. Because we want to find what is the stress here and the stress here, which is B is minus, right, minus 50, and point C is plus 50 distance from neutral axis. So here you have to be careful, neutral axis is this one, all right? And you find the moment of inertia I about that neutral axis. So that's why this 1/12, this is B, this is your H. So check why the B is 40 and the H is 100. You have to check why this is 40, this is B, right? And then this is H. So check that one, why? I mean, at this point, you should be able to do that. Otherwise, you should go back to chapter 6 and check that again. Okay, and then you get this value 11.25 megapascal, the maximum bending stress at B and C. Can you see that actually at B you will have positive, which is tension bending stress, while at C you have compression bending stress minus. So, okay, and then okay, this is the superposition stuff. Due to the P, you will have this kind of distribution, the uniform distribution of compression, compressive stress, bending, compressive normal stress, 3.75 megapascal. Okay, uniform at any point, right? And due to the bending moment, into the bending moment M, you have this kind of distribution. Can you see that? Like I said, at point B and along this line, okay, you have 11.25 megapascal, which is in tension. While at C, you have 11.25 megapascal in compression. All right, and it will be zero at the neutral. This neutral axis, right? Can you see the distribution? So if you superpose them, what happened at point B? Point B, this is minus 35, right? For point B, okay, is minus 3.75, okay, plus 11.25, and then you will get this 7.5 megapascal in tension, which is positive. All right. Again, why this is minus 3.75? Because it's a compression. Okay, compression. Okay, and you can see that for C, the C at point C, due to normal force, it is minus 3.75 because it's compression. And due to the bending moment, it is minus 11.25, minus as well, compression as well. So you sum this up, you get 50 or minus 15 actually, but it's fine, 50 megapascal, but you must tell that this is a compression. All right, so that's why I said this tension and compression, you need to be careful. I mean, the direction, whether, because if you cannot here you cannot just simply sum the magnitudes. Okay, that's not correct. It's very incorrect, because you need to see whether it's in tension or compression, right? And then it's not in the question, but actually you can find where is the zero. I mean, it will be, you have, because you you superpose this, right? Then you will have this kind of stress variation, normal stress variation across the cross section, and you can find where is this zero stress, right? It's not at the neutral axis anymore. Neutral axis, the zero stress you have to superpose with the axial stress, right? So now the zero force, so zero stress will be shifted to somewhere, which is this. I mean, you use this proportional triangle method to find the location of this x, right? Although actually it's not in the equation. Okay, so if you want to draw the volumetric element, okay, the stress state in the volume element. So at C, sorry, at B, C here means that compression, okay, not the point. At point B, you will have tension of 7.5, right? Like this. And at C, okay, you have the compression of 15 megapascal, right? And you have this example 8.4. You can look at this example on how actually it works. Now here you have more internal loadings, right? If you cut at C, you will have more internal loadings. You have here, you have axial, right, or normal force, whatever name you prefer. You have internal bending moment as well, M, and you have this shear, transverse shear, right? So now you have three internal moments. You don't have torsion here, but you have these three, right? So you have to find individually sigma at point C due to the internal P, right? And then sigma at C due to internal moment M, right? And then for these two, you can sum them up. right? I mean, depending on whether it's tension or compression or those other we discussed, we can superpose. Okay, here the one the solution here does not discuss on the V, but actually you okay, the V here, the shear stress due to V here will be zero. Actually, it's a trick. There is shear stress due to V, but the location of this point C will make the shear stress as zero, right? There is a, you see this distribution, shear stress distribution, because the shear stress, the the equation for the shear stress tau equals to VQ over IT, right? In chapter 7, the stress shear, the maximum value of tau will be at the neutral axis, right? And the zero value will be at the for this distance, which is this and this, right? So that's why zero. But don't take for granted there is a shear stress. It's just the location of C. At the location of C, you will have shear stress, right? Okay, and then for this P81, P82, and all this F82, we'll inshallah we cover this in the tutorial, right? Okay, that's all for chapter 8.